chip connectivity for energy efficient AI computing.
Great, thank you. Thanks, Dan, and thanks to the organizing committee for the invitation. It's really great to be here. So I'd like to start off with, this worked before, but now it's not working. You know why it's not working? I can use this for now until you get it. We did test it. Okay, it's okay. I can use this. It's all right. Okay, now this is not working.
Right.
Okay, now it's working. Okay.
Yeah, I think it works now, basically.
Okay,
To
great.
write all this about.
Okay, got it. Okay, great. So this is the obligatory chart that we now have in all our slides, showing the enormous growth of AI application, machine learning application. You see some of the familiar workloads. And as we know, the growth rate has been tremendous, maybe something like an order of magnitude per year in the last 6 years or so. It looks like it's continuing. Maybe at some point this will level off, but for the moment, this incredibly huge rate of growth in the size and the parameter numbers as measured here, and we're getting close to 100 trillion parameters. And the key that we take from that number or from that growth for the purposes of photonic connectivity and optical networking is that the large workload really does not fit in any one compute element, compute node, or even small cluster. So necessarily we need to connect many of these computing resources together, computing resources with their memory together. And this is where, at least in our view, photonics has a role to play, photonic networking and interconnection networks. At the same time as the growth in the parameter size of the workload is occurring, what you see here is the energy consumption associated with training these very large models, right? And this is also pretty well known. And we've predicted this unsustainable energy consuming aspect of AI systems. And I just want to kind of put a little bit of a frame of reference for how much power this is taking. So I plotted a line for approximately the amount of power that's delivered to the entire city of New York City, large city where I live. So about 5,500 megawatts, right? Megawatt hours. And this is, you see some of the very large models are still below that. And even if we look in the middle of the summer, like we are right now in New York, it's, when we all have our air conditioning on and so forth, we're talking about maybe 32,000 megawatts, right? And GPT-4 is even above that. So it took about between 90 to 100 days to train GPT-4 on A100s, the NVIDIA A100s. And this is over 51,000 megawatt hours, right? We all enjoy GPT-4 and so forth, but the amount of power, it's not just a small thing anymore. And many of the many of the operators are indeed talking about nuclear power for data centers. It used to be something that we just kind of thought was a joke, but it's not. So the power consumption is a real thing. I mean, it's an economic thing as well. This costs power. It just costs money to run. So having said that, the goal, the idea here is, can we bring photonics to the data center, and where does it need to be, and what are the metrics associated with bringing photonic connectivity where it can actually make a difference and have an impact on the execution time and thereby also on the power consumption associated with the system. So let's look at what the numbers are in today's high performance AI systems. If we look inside the socket, we have extremely high bandwidths inside. This is all electronic. inside the socket, you see, like, for example, in the NVIDIA DGX, nearly 10 terabytes per second of connectivity. And this connectivity is also extremely energy efficient. It's actually quite good. You know, within the chip, within the 3D stack, the numbers are in the single femtojoules per bit. So extremely, extremely efficient. Once we get a little bit outside of that, you know, with the NV switch or similar fabrics within the socket, so to speak, that's how at least we refer to it. So the GPU bandwidth is maybe 1 or 2 terabytes per second today. It's also, you know, all these numbers are continuing to increase as advances are made. But at the same time, they're kind of reaching their limit because there's so much, so much electrical connectivity that you can put inside of the chip, right? We cannot put the wires too close to each other because we're running to crosstalk, especially at high speeds. So there's a limit here that we're getting very close to reaching. The NVIDIA NV switch, for example, is, you know, a few hundred gigabits per millimeter, and that's kind of where it is. It's not really getting much better than that. And speaking with some of the folks, we have collaborations with them, you know, the yield is just getting worse and worse. So it's just reaching a limit to how much bandwidth density you can get. But pretty much within the socket and within the chip, the numbers are good. The problem starts to happen when we take the data off the socket, off the board, and start to communicate over longer distances, still within the data center, but over longer distances. And you see here, we resort to commercial sort of pluggable photonics. So 400 gigabit InfiniBand, maybe 800 gigabit in the near term, maybe even 1.6, right? But it's still pending, not widely deployed commercially yet. Still, these numbers between what we get, you know, inter data center and within the socket or within the chip is over 2 orders of magnitude in the bandwidth difference, right? So if we want to bring photonics in, we need to, the goal here is to basically close that gap, right? We need to bring photonics into the socket, perhaps, or even further into the chip, you know, be able to achieve those extremely high bandwidth densities, while at the same time achieving the energy efficiency. So a good way to look at it is this chart over here on the left side, which is adapted from Gordon Keeler, part of the DARPA PIPES project, which I am leading one of the teams. I'm also part of the Intel team under the PIPES project. So we have a lot of involvement here. And what you see here on the left side is essentially a metrics chart that shows on the vertical axis, the metric is how much bandwidth density do you have and how energy efficient are you? The higher you are on the y-axis, the better, okay? And the horizontal axis is the distance. So very simply, if you look to the left side of that chart, right, that green square, for example, is the most advanced electronic connectivity, the things that I showed you on the chip, GPU to HBM to high bandwidth memory and so forth. So extremely high bandwidth density, those are great. You know, within that chip, 3D stack, the pitches can be made very small, and the energy consumptions are on the order of singles of femtojoules per bit, maybe up to 10 femtojoules or so. Incredible good numbers. However, the problem is once you start to propagate any appreciable distance in the electronic domain, of course, we start to deal with losses and so forth. And once we get to the data center, the internode connectivity, where we have to scale these, you know, like the GPT-4, you know, 20,000 clusters. So we have to scale and propagate the data over longer distances. You can see that the metric starts to fall down. And even those purple diamonds that you see there, those are optics. Those are the commercial pluggable optics that we have today. So why isn't optics up, you know, further up there on this chart? You can see a little bit of an example here, the Terafy. That's a product that's out of a company called IR Labs that does use integrated photonics to do that. It's not quite where we want to be, but it's a really nice step in the right direction. So these pluggables were simply not designed for bandwidth density energy efficiency. They're kind of They sort of evolved from the telecom days. And, they're great, they're very useful, and they will continue to be very useful in data centers. I'm not saying that those pluggables are leaving the market, but we need to bring, and you can see the picture down here, this is the pluggable, and this is where the socket is, and we have these kind of long PCB traces and all kinds of issues that limit the bandwidth and the scale. So what we want to do is kind of go to the top right picture there, where we closely integrate the photonic chiplet, the photonic IO chiplet, with the compute resource, with the memory resource. And so what that enables us to do is achieve the high bandwidth density and the energy efficiency both at the same time. That's the challenge. It's not one or the other. You really have to achieve both at the same time to make sense. And then once we can put the photonics there in this either chiplet model or however the packaging needs to be, then you can imagine connecting with the same high bandwidth density that we have on the chip today, but now being able to propagate that data across the entire data center, maintaining a constant, very low energy efficiency or the energy per bit, right? So that enables things like disaggregated architectures and really selecting the resources that are needed for the application, maybe with optical switches and so on. So this is where we're going. So technology-wise, from this, the way to get there, at least from our view, is through integrated silicon photonics. This is the way to get, large densities, production, mass production. We can put photonics on a 300 millimeter wafer and fabricate it in the same CMOS, in similar CMOS fabrication foundries that exist today. So economically and really practically, that's really the best approach that we have today, right? There's no other photonic technology that scales like this. Indium phosphide, way too expensive, lithium niobate, there's no way you can do this in lithium niobate. Although they each have important application. I'm not dismissing any technology, I'm just focusing on this specific application. So, okay, so silicon photonics. So what do we do? How do we get bandwidth density in optics in an efficient way? Is by using the wavelength domain, by using wavelength division multiplexing. And to be able to get bandwidth density and lower energy consumption, we want to actually drive each of these wavelength channels at relatively modest rates, right? The energy will grow with the higher speeds. If I run at 100 gigabit, it's going to require, the sensitivity of the receiver will be worse, much worse. And so that will require much more power and much higher power for the driving circuitry of the modulators. So higher data rates, serial does not really work well here. I can't get both to happen. So I need to be able to spread my data over as many wavelengths as possible. It's very similar to the multi-core architectures, right? We stopped scaling the CPU frequency a long time ago now. Back in the day when I was young, we actually expected the PC to double in frequency every 18 months. That has long never ever happened. So you guys are in the generation of the multi-core, so to you it maybe seems like natural, but it's very unnatural. This is the same thing that's happening here with photonics. So we're scaling with the wavelengths instead of single wavelength, higher speed for this application. So once we get there, if we're able to do that, we can imagine this distance independent bandwidth density energy consumption. So to be able to get lots and lots of wavelengths, you also need to pay a lot of attention to the laser source. How do you generate all these wavelengths, right? If you use, let's say you need 100 wavelengths, if you have 100 lasers to do that, that's going to require a tremendous amount of power. The yield on getting 100 different lasers to line up exactly where you need them economically is a non-starter. It's really a non-starter. So really the approach is to use a comb laser technology, and that's a very important enabling component. You can see up there, this is work that's with my collaborators, Alex Baeda and Carl Lipson. This is a packaged comb, so it's a single chip. It's actually silicon nitride chip. It's pumped by one laser. So it's really one laser that generates many, many wavelengths at the same time. This is an example of a recent comb that generated 70 channels. We have better combs right now, but this is just an example to show you. And it has very good conversion efficiency, 46%, which in this example translates to a wall plug efficiency of about 12%, which is pretty good, pretty good. You know, just by comparison, the conventional, you know, telecom DFB laser is kind of in a single percentage wall plug efficiency. So this is very good. We care about all these efficiencies because we're going to be counting femtojoules. So every single place matters a lot. The next is the modulator for the transmitter. And what's really important here is that, you know, you try to design a modulator that can modulate these different frequencies, of course. So why do we choose a resonator modulator? Because we don't want to have to do the wavelength demuxing, right? You start with the comb. If you use the Mach-Zehnder modulator, for example, let's say, you would have to have some kind of a wavelength demuxing element in front of that, a WDM of sorts, right? AWGs, and then separate all the wavelengths, modulate all the wavelengths, recombine all the wavelengths. We don't want to do any of that because it's going to cost us bandwidth density, just the footprint of all this stuff, and it's going to cost us losses. Losses translates into more energy. Every loss in your link budget means more energy. So we choose a ring technology which does both the wavelength selectivity as well as the modulation at the same time. But rings are not good enough. We have to do discs. Why? A few reasons. Number one, the discs can be driven with much lower voltage. We have a vertical junction in those discs. These are custom designs. You see a few evolutions of that. At the bottom, you see a 32 gigabit eye from our recent discs with 0.8 volts peak to peak. We specifically wanted to go very low voltage because we want it to be compatible with CMOS technology. Sometimes you open up, people talk about silicon photonics, you open it up under the hood, it's actually driven with like 1.5 volts or even 2 volts. And it's a non-starter because advanced CMOS is not going to do that. And it's certainly not going to do that energy efficiently. I'm very excited because our latest results on these modulators, I couldn't believe it, so I still have to verify it. But my students just got a recent run back and were able to generate the same eye with 0.2 volts peak to peak. So these results are, I didn't put them down because they need to be confirmed, but it's just the geometry of the vertical junction with the disc that enables that. The second reason is that with a disc, you can make the device very, very small, which means it can have a large, what's known as free spectral range. So you have a broad bandwidth that you can handle where you can put in a lot of channels. We can even go beyond that with something that we call the multi-FSR regime, but just putting that aside, you want a device that's very broadband. And lastly, the fact that it's a disc, and you have a whispering gallery mode, you only really have one edge to worry about in the fabrication variation. When you have a ring, the light is contained into the waveguide of the ring, and so you have two edges, right? Two rails, and you can have fabrication variations. So because we only have one edge here, it makes a huge difference in the statistics of the fabrication variations, and it makes the devices very robust. That means you need to use less thermal energy to tune them, which is, again, another component of our link. So just an example of that. It's fab robust, it's very efficient, and the free spectral range very closely matches design volume. So what you see here is the spectrum of we have in this particular link, we have 4 times 16. So this is a 4 terabit IO chip. This is the one that we're doing with Intel. But the only point that I'm showing here is that all these disks were designed to be at a certain wavelength, and untuned, they're not exactly perfect, but they're coming very, very close. So the amount of tuning that you need to do is very, very small. If we do the same experiment with rings, what happens is they're all bunched up to the left. That's what happens. You take out your ring, you look at the spectrum, and you're like, oh, I have to tune them over, okay? So this is the advantage of the disks. Very fortunately, we are able to get what's known as a full reticle designs that we are able to do, as opposed to multi-project wafer NPW runs. So we do these 300 millimeter wafer designs, active full stack. So this was our very first one. We call it Cedar. We used to do a lot of NPWs. We still do some. But then when we started to do a full custom reticle, which of course costs a lot of money, my students got very, very spoiled, you know, and like, because now they have lots of space, they don't have to constrain themselves to a certain area, and they can design whatever they want. And so I sort of, you know, I didn't want them to get so spoiled, but now they're spoiled. The downside is it takes a long time to, you know, this is a lot of work to get this kind of design out. So they also get very good experience. So we did this run, we got some results back, and then we had enough funding to do a second. So this is already a second full reticle run that we did. We called it Oak. You can see more variations on these over here. These are all the detail links that are part of that. And then this wasn't enough, and actually we did a third full reticle. And this is the one that we just got back. I can't tell the days anymore because it took me like 3 days to fly here, right? So we got it back about a week and a half ago. So we're very excited. It's fabbed out, called Willow. You can see, you know, many variations on the designs. So I'm just showing these because this really enables you to really statistically really dial in these designs and to really squeeze out all the performance, as well as get real statistical data, right? It's fine to do one device, but to do statistical data so that you can think about, you know, because the number of links that would go into these AI systems will be many, many links, right? It's not just one paper. So you really need to think about the system level implications of all that stuff. It's just summarizing our approach. We embrace parallelism. We run, you know, we use the comb laser technology to enable that. By the way, for laser people here, this is a normal GVD comb. That's the reason it can generate a lot of wavelengths and relatively high power per wavelength, unlike a soliton comb or a quantum dot comb or other technologies. Then the scalable architecture, and then the reduction of the thermal energy that's required to tune all the devices. We also have, I didn't show it, but we also have disk filters to match the disk modulators, but also to reduce the amount of tuning. So then we take it all. We worked with a collaborator at Cornell, Al Molnar, professor there, who designed an EIC to drive all these modulators and receivers. And because we had the ability to fabricate at the full wafer, right, we could do die-on wafer packaging. So that enabled us to do very high density pitch for the connections between the EIC and the PIC. And also to reduce all the parasitics, right? 3D is a lot better than 2D or 2.5D. And so the EIC was, again, designed by Cornell, and it was just fabricated at TSMC 28. So it's a very conventional, nothing really special about the electronic chip. Very, very low cost and conventional. And so this is a picture of the full 3D integrated chiplet, photonic IO chiplet. And each of the modulators here is running at a modest 10 gigabit per second. It's actually limited. I showed you that they can go to 32, but they're running at 10 really because that's as fast as the EICs can run it. That 28 nanometer EIC can really only push about 10 gigabit, maybe 12 at the most. So we ran it at 10, but even at 10 gigabit per second with 80 channels, we're getting 5.3 terabits per millimeter squared. So that already is a record bandwidth density that's possible here. You can see because we're able to get the full wafer, you know, you can see the pitch here, right? The EIC and the PIC, and it's 25 micron pitch. It's not anything, you know, earth-shattering. People can do wafer-to-wafer bonding, but it's not possible to do that with a die, with a single die. And the energy consumption here is about 50. It's about 50 femtojoules. It says 70 femtojoules. It's about 50 femtojoules for the TX with all 80 modulators running, and about 120 femtojoules for the RX with all receivers running at the same time. So it's just under 200 femtojoules for this transceiver. And I'll show you how all the energies add up together with the laser and with the thermal consumption. Right here. So this is an analysis. This is a link energy breakdown based on those measurements. But now the measurements are actually based on running the modulators at faster rates at 32 gigabits per second, the full rate that they're running, as well as the receiver. 12% wall plug efficiency for the laser, 0.8 volts peak to peak. In this case, we have over 5.4 terabits per millimeter, not per millimeter squared, but this is the edge bandwidth density. And you compare that to today's like NVLinks or any of these high density connectivity in electronics, which are maybe 400, 500 gigabits per millimeter, right? So this is a really nice, factor of 10x already on the bandwidth density. And we add up all the energy consumptions of the comb, the thermal, and the transceiver, and we're just, under 400 femtojoules per bit. And we can probably push that a little bit better. But the comb is taking up a big chunk. So that's one area where we really need to try to drive it down. Okay, so the vision again is that suppose we could bring this connectivity into the component, into the resource, whether it's the GPUs or actually very interestingly, the memory, right? I mentioned at the beginning of my talk how over 100 trillion parameters in these workloads, in this parameter space, they're not going to fit. Typically you have a couple of GPUs and maybe 9 HBMs around your interposer. You cannot put that much data, right, in one socket. And so what if but because you're limited by the size of the interposer, right? Anything beyond that, the electrical connectivity is gonna drop off a cliff in terms of the bandwidth density. But if we have photonic connectivity, we can imagine creating these memory interposers with photonic connectivity directly to the HBM. And having many of them, right, connected together so that we get to both increase the memory capacity and maintaining the high bandwidth, memory access, right? Of course, there's always a limit, and the limit is going to be latency. So at some point, the propagation latency associated with moving the data from the GPU to memory and back, as we expand the circumference of the system, is going to start to play a role. And it's going to require people that are from the architectural level, from the algorithmic level to manage that, right? Because we can't do too much about the speed of light. So it will become a limiting problem. But there's a lot between now and then. There's a lot to be gained still. And then when we think about the network as a whole, right? We want to maintain the data in the optical domain, and so optical switching come in. I know there's going to be a great talk right after mine of really advanced optical switching that's being done in data center with the two Georges. What I want to show here is we're looking at some photonic switches that can be done in the same platform as the transceiver. So we're looking at these kind of can we add photonic flexibility to the transceiver itself, right? So you have a transceiver with maybe 128 wavelengths. Can you then, send, 16 this way, 32 that way, and reconfigure within the IO, have multiple IOs. And so the technology that we're working on is essentially a microring based spatial wavelength selective switch. You can see the architecture kind of briefly up there. I'll just say that it's a very scalable architecture from the point of view that the losses scale very well because we can put we have two layers in the switch, and you basically only go up to the switching layer when you need to switch. So the rest of the propagation happens in the silicon nitride layer. So you can make the switch, it's still a linear 2D switch. So it's not going to go up to 1,000, but I think realistically it can go up to maybe like a 16 or 32. Maybe 64 if you really push it, but that's about it. It's not the kind of thing it's not like a 3D MEMS that can scale much more. So with this limited notion, that's the reason we're thinking about it more like a locally within a cluster, not for the very top of the switch. But again, the thing that's unique here is that it's completely wavelength selective. So for example, this is a small example. This is just a 4x4x4 switch, but I can come into any of these 4 ports with 4 wavelengths and completely reconfigure them in any way I want. I can also do multicasting, I can do broadcasting, I can do selective switches, however I want. It's completely, and it's actually worked. You can see here some of the bit error rates for all these, for different configurations, and they really sort of lie on top of each other. And just one more picture here. This is kind of fully loaded, with all 4 ports loaded with all the wavelengths. And we can essentially shuffle, reconnect them in however we decide, with really, really decent performance. The crosstalk here is very, very low. So just a little example of another device that could be used in the system. Still, work to be done there, obviously. All right, so this is going back to kind of the vision. The first step, which we really put the most work into, is let's bring the connectivity right into the socket, right? So we can now think in the optical domain for the rest of the system, and we did it with really good energy efficiency and extremely high bandwidth density. Otherwise it doesn't really make any sense to do that. I just want to mention quickly that I'm also leading a center that actually, supported part of this work that I mentioned, and it's been a real pleasure. We have, I think, like maybe 12 different universities that are included here, led by Columbia, and many are really the luminaries in the field. What I really like about this is that it brings together both wireless and wireline photonic communications. So we all kind of are talking to each other, at least. We're not really completely there yet. Still have some work to do on merging the fields, but it's really nice to to have all these expertise under one umbrella. So this was launched last year, and it's a nice big program. So it really enables you to do a lot of work. Just want to thank my group and the sponsors, and these are the different companies that are involved in the Jump Center. So you can see that really good to have their input and support. Okay, so with that, I can stop, and thank you again for.
Questions?
Okay. So how do these things SerDes? You're
SerDes-
talking these things at 10,
Yeah.
the clock rate's at 3. How do you get no SerDes?
The SerDes is, I agree completely,
Okay.
so in terms of, obviously to go from 3 to 10, you need to SerDes it out.
Okay.
This is really more of, the connectivity that you have at the edge of the socket, which is has already been dialed up, right? It's already been dialed up to go over longer distances.
Okay.
So we're
So you
just
compare
not
it to
counting it all the way down. Yeah.
So you're comparing to, say, a standard electrical SerDes?
I mean, the electrical chip that I showed you, right? It also runs at essentially 2 gigahertz, and it has the SerDes in it as well to bring it up to the 10.
Okay.
So, and those numbers are included in the energy numbers that I showed.
Okay.
But what I mean by the SerDes is that, we're not requiring like to go to 100 or that number. But fair question.
Questions?
It's what the market.
Could I ask a question?
Wondering with the thermal console, what's the temperature coefficient if it wasn't there?
Yeah, so the thermal is always an issue, right? And so the way we do the thermal control is we have essentially we have resistors or microheaters that are integrated into all these devices. So the disk, for example, I didn't have a chance to go too far into it, but the disk has RF, all the RF contacts are inside the disk. On top of that, we also have a heater inside the disk that has like a DC, contacts that are applied to it, and essentially change the index of refraction to be able to, control the resonant frequency of that disk. More recently, we're able to put the heater actually outside of the disk, but at the end of the day, there's always going to be some amount of thermal, control that you need to have, especially if the whole module is operating over a large temperature range. As you know, every optical device is temperature sensitive in one way or another. And so what we try to do here is reduce the amount, not reduce it altogether, so it's not zero, but just reduce the amount of tweaking or turning that you need to do to get it to the right frequencies.
So we've got question online yet? Do they ask it or is there a way to see? it?
Zhizhen,
Yeah,
you can just ask.
can you hear me?
Yeah.
Yes, we can.
Yeah, so Karen, could you also provide your comments or perspectives on the compatibility with protocols like PCIe or CXL? Or another way of speaking, are we gonna have PCIe over optics or CXL over optics?
Yeah, that's a great question for those that maybe didn't hear on the compatibility with different protocol like CXL or PCIe. So in general, the concept is that we would have the photonics over, over whatever the protocol underneath it. We have done much more, there's a lot more sort of interest and effort on the CXL. The PCIe is just, it's kind of, to be honest, it's kind of a bear to work with for those that have worked with it. It's like it's a difficult stack and all the all the layers all the handshaking and layers that need to be done, somehow they take out the advantages that you get from the photonic layers, at least in our experience. But the CXL is certainly much more friendly, if you will, to the photonics. But just kind of at a fundamental layer, it doesn't really matter. You can operate any of these protocols on top of the optics.
Awesome, thank you.
Sure.
Question? Yes, thank you.